Are there any questions then about, let's see, about the exam? I think there was one comment about the exam. Somebody had looked up in Chapter 10 about, there's a formula for the VIF, the J'th variance inflation factor, and there's a formula in Chapter 10 that's displayed, and I just want to make a warning about that formula. In section 10.3, let's see, where's that formula? I'll find it here in a moment. 337? Okay, yeah. It starts on page 328, effects of multicollinearity. What he's doing in the section 10.3, where he displays the formula for the J'th variance inflation factor, is he's assuming that the X matrix is determined when x1, x2, etc., the regressors are scaled to unit length. Okay? So actually, X is only an N by K matrix. So in section 10.3, page 328, you have X is only N by K, not N by P. Okay. And there's no column of ones. It's x 1 1 minus x1 bar over, let's see, I think he's going to unit length, so that would be an S11 with a square root sign. Okay. Down to x n1 minus x1 bar over the square root of S11. All right. So the generic term is xi1 minus x1 bar in the first column. Okay, I goes from 1 to n. Okay, xi1 minus x1 bar over the square root of S11. Okay, capital S, well, that's the variability of the first variable. Okay? It's not a very sharp pen. Maybe make it a little bit bigger here so you can see it. xi1, and then so on down to xn1 minus x1 bar over the square root of S11. Okay? That's the first column, then you have the k columns. So xk1 minus xk bar, excuse me, x1k minus xk bar, that's the way we did it, over the square root of skk, down to xik minus xk bar over the square root of skk, etc. So this is n by k. And then what you're getting is that x prime x is the correlation matrix. Sample correlation matrix. So this is R1, 1 down to R K, K, and R, the J'th regressor with the Lth regressor in general. Okay, RJL. J and L going from 1 to K. So you're taking the regressors, that's the correlation matrix for regressors. So that's the thing to remind yourself of in this chapter, or in that section. And so he actually gives you the C matrix correspondingly. C is x prime x inverse. Okay, is our usual formula, but that's the C for this unit length scaling. All right. So the regression model is y0 I equals b1. What we called this, I forgot what we called this. x I 1. I forgot what we called those variables. X after the unit length scaling. X prime, or what do we call them? Oh, we call them W's, I believe. WI1 plus and so on plus B K W I K. All right, plus errors. And so this is really what we called before the W prime W inverse matrix. Okay. Well, this is the WK column. This is the W1. Okay. So just note the fact he's calling it X. He really should have called it W from the earlier chapter. But he just says, okay, we'll call it X now because I don't feel like changing the W's for the whole chapter. Is everybody clear then? So you have to, if you're going to use that formula, then you have to put in the correlation matrix and take the inverse, and then you get the variance inflation factors on the diagonal of the inverse of that matrix.
So we can use the equation on 119.
Yes. So VIFJ equals the JJ element of this correlation matrix to the minus 1. Well, correlation matrix to the minus 1. Yeah, you can use regression of the jth regressor on the remainder. Take 1 over, and there's a formula for it. JJ element of this thing. This is the correlation matrix. Correlation of regressors. Which turns out to be equal to, this is a nice, I guess it would be a little linear algebra problem, which is 1 over rj squared, where you, this is the multiple, this is the r squared coefficient for regressing xj on the remaining regressors. Equals r squared for regressing xj on remaining regressors.
Is there an easier way to find those values other than actually doing all those different regressions?
Well, yeah, just calculate this you can with one hit of the button you get the correlation matrix. The only problem is it only gives you half of the. It only gives you the lower triangular. It's a symmetric matrix, so Excel only gives you this bottom half. So you have to copy and paste this top half, which is kind of a pain.
So there's a correlation matrix?
Yeah, there's a correlation function. Okay. Under the data analysis tools, you can get the correlation. But you have to fill in some of the entries still. Okay, but still, it's a small matrix because it's only k by k. It's only k by k, so there's only a few entries to fill in. Then you can take that and invert it. So that's fairly simple. Ways to get the variance inflation factors. Okay. So you don't have to do all these regressions. Okay. Everybody follow? That was the one key question on the exam that will probably cut down the computation time quite a bit.
Oh yeah.
Anything else from the exam? Okay. Let's talk about polynomial regression then. Okay. Let's see, hand out some notes. I have a few notes here, and those out. Oh yeah, thank you. We consider now a polynomial where the regressors are monomials in some independent variables. So I might have one independent variable, I might have two independent variables, and so on. So think of a function of one variable, a function of two variables. Okay. plotting the surface and so on. So you have some kind of response surface. You have an input and you have a response. And so we'll have a graph in 2 dimensions for the, x versus y. It's just a single independent variable. Or we'll have a graph for the response surface in 3 dimensions if there's 2 independent variables and a dependent variable y. Everybody following? Okay. So we're going to consider we're just going to something where we've already pretty much considered y equals, in principle, a model of this type where this x is a single independent variable. Or you could consider, or more generally, consider y is beta 0. I'm mostly just setting down the notation. Beta 1, x1. If I have 2 independent variables, is how will I index the betas? Well, a natural way is to put one index for each linear term in the variables, and then do double index for beta 1, 1, x1 squared plus beta 1, 2, x1, x2 plus beta 2, 2, x2 squared plus epsilon. So this is a full quadratic regression function in 2 independent variables. So if you had 2 independent variables and you wanted a full quadratic response surface, you would use this. And of course, I don't have to have all the terms there, and I can have plus etc. if you have that, plus epsilon. Okay, plus etc. In other words, I can have higher order terms. I can skip terms and so on. Now, the author made some comment about hierarchical models. Let's put this in. Also, sometimes what happens if I replace, what you're going to get is sometimes you get that there's a lot of correlation between the regressors. Because what are the regressors? The regressors are 1, x, x squared. Sometimes that gives you a lot of correlation. So, for example, if I had x between 1 and 2, the point is if I had x between 1 and 2, let's say, and I had a column of 1s for my intercept, then I had my x 1, 1.1, 1.2, let's say down to 2.0, let's say there were 11 observations. Okay, n equals 11. Okay, just for instance. And then x squared would be 1, 1.21, 1.44, and so on down to 4.0. You can imagine that the correlation matrix has a lot of high correlations in it. Okay. Well, so why is that a problem? Well, it becomes a problem for the machine if you have too many high correlations in terms of inverting the matrix. You start getting round-off error and so on. That doesn't seem like a big deal nowadays with the way machines are. Fast, you can put your epsilon as small as you can put your machine epsilon pretty small, but it does kind of counteract the round-off error problem. Okay. Now the author also mentioned something about variance inflation factors, but that I'm going to put a kind of a caveat on that, as we'll see in a second. Because so note that 1, y equals beta 0 plus beta 1x plus beta 2 x squared plus epsilon is equivalent to 1 prime. What I'm going to do is define x prime equals x minus its average. Okay? It's not a unit scaling, it's just a centered scaling. Okay, so center, or it's a centering. There's no scaling. It's a centering of the regressor. of the independent variable, is equivalent to 1 prime, y is equal to beta 0 prime plus beta 1 prime x prime plus beta 2 prime x prime squared plus epsilon. These are the same regression models. All you're saying is that here I have a quadratic function to fit my data. Here I have a quadratic function to fit my data. I can take when I estimate the betas, I will find the best fitting quadratic function in 1. When I estimate the beta primes, I'll find the best fitting quadratic function. In fact, what's the relationship? Since x prime is equal to x minus x bar, the beta 2 prime is equal to the beta 2. The coefficient of the x squared is the same, right? Should be the same. So actually beta 2 equal to beta 2 prime. We'll see this in an example in a second. And just take a baby example and work this out. Okay? However, the only point of this is that if I do that centering, note that the hierarchical model, the non-hierarchical model, how do you spell hierarchy? I think it's this, H-E-I-E-R, Kako. Non-hierarchical model.
Which one's the hierarchical?
We'll see. The hierarchical means you put all the powers in. Okay, you don't skip any. Not hierarchical model. Y equals beta 0 plus beta 1 x plus beta 3 x cubed plus error is not equivalent to y equals beta 0 prime plus beta 1 prime x prime plus beta 3 prime x prime cubed. Okay, because now I don't have a full cubic fit. Okay, these are different models. Okay.
See what the correct spelling is?
Yeah, maybe. What is it?
H-I-R-A. The A between the R and the A.
Huh?
A. R. C.
There's no CH, huh?
There is H. H. And everything else, right?
Blah, blah, blah. Okay, I can't spell. I have it wrong. I don't know what the problem is. Oh, I see. Huh. There's no H-E-I-E, huh?
It doesn't matter.
Okay. H-I-E-R. Okay, I got it. Yeah. Yeah, I have too many. There's no H-E-I-E probably in the whole English language, right? Okay. All right. I'll find it. Hierarchical. Okay, so the first E was no good. Everything else was basically okay, right? Okay. Now, it's not equivalent to those, so just be aware of that fact. Okay. Now let's have a look at exercise 7.4. Let's go ahead and look at exercise 7.4, which is also on the website. I have to unload it. Okay, download it. Exercise 7.4. The picture come on? Okay. Just have a look at this thing. There's also another little problem, 7.2 on here. Now on this one, I just got tired of doing linear regression with the data analysis tool, so I used a different function. linest. Okay, which is an array formula. I just thought I'd mention it here in this example. Okay, so problem 7.4, you're just given some data here, the x values, and then there are the y values. Okay, and they ask us to just fit a quadratic model to this data. I'll just go ahead and read the problem. And I don't know where they came with these data, whether they made it up or what, but it came out kind of interesting anyway. Could have been cooked up. Consider the following data. Fit a second-order polynomial model to these data, test for significance of regression, test for lack of fit, and comment on the adequacy of the second-order model. Test the hypothesis beta 2 equal to 0. Can the quadratic term be deleted from this equation? Okay. First, I'm going to do the lack of fit analysis. Since x is repeated 3 times, x equals 4 is repeated 3 times, there are 3 y values associated with it. So what am I calculating? I'm calculating there's 2 degrees of freedom associated with that, and I'm calculating twice the standard deviation squared. There's another, that's an alternative formula. I could have used equals twice var, right? And I should get the of these 3, right? Should get the same number, 0.0386. I mean 0.386. Okay? So it's just a different formula. Okay? Same thing. And I calculated the pure error, and it came out to only the SSPE. This was SSPE, right? Only came out to 0.4, whereas actually this is my little table of all this data from the multiple regression. Now I note that when you do this array formula, what it is that this is there's a certain array formula here, which is namely this. It says line est D6 to D17. That's the y's, okay, with no labels. B6 to C17. Here I'm not centering the x values, so it's just these is whatever. What did I do? Okay, let's go back to my array formula. B6 to C17 true means I wanted all the stats. Okay, true. I mean 1 1. I think you can also put in there. Look up line est in the help topics. I don't want to do it here because it's going to load Microsoft Professional Help and takes forever. Okay, so true means you can just put 1 1 in there. That means it gives you everything that you can get. Namely, it gives you not only the coefficients, the beta hats, which are given in descending order automatically. That's the default here. So I've added these labels myself. This I added. Okay? It does not give you any labels. It just gives you numbers in an array. Okay? So you have to memorize this or keep a template around for actually what is going on in this table. That's the only problem. Otherwise, it's nice compact information. You don't have to look all over the place. Standard errors of the beta hats. Okay, R square for the model is, hey, this is 99.5% of the variation is covered.
What's that second value mean?
S. That's the means. That's SS res divided by the degrees of freedom. It should be the 20 with the square root on it. So 24.72 divided by 9. 24.72 divided by 9. Then take a square root. You get this. All right. That's the S. So actually, that's duplicated information. You figured it out, but you needed to have it somewhere because in the F for regression, that's 1045. That's a regression F. Okay. These are the T statistics are associated with these, right? Where are the T's? Did they give you any T's or p-values? No. You have to calculate the T's yourself by dividing the beta hats by the standard errors. Then you get the T statistics. Okay. So here I did it, in fact, over here. Beta 2 equal to 0. The T statistic is 1.467. Notice that these two numbers with the beta prime, beta 2 prime is equal to beta 2. Okay? These two numbers are the same as I said they would be. Okay? This beta x squared is beta x squared. Okay. The beta 1 in prime is not equal to the beta 1 because there's x bars coming in. You know, if you do x minus x bar squared and do some other stuff in there. Okay? So, okay, what was I doing? Okay, so then you take 1.467 divided by the 0.4936. This divided by that. In fact, that's what I think I did over here. I said H24 divided by H25. That's H24. This is H25. H24 divided by H25, that's my T statistic. It's nearly 3, so even with degrees of freedom funny, that's going to be significant, at least a little bit. Okay? I didn't calculate the p-values. So all the p-values and all that stuff has not been calculated automatically, which is kind of a nuisance, but it's nice and compact. Okay. What about the lack of fit then? I took this SSPA, had my S-res is 24.72. This 24.72 is the residual sum of squares. Well, most of that is due to the lack of fit, apparently, according to my pure error estimate of sigma squared. My pure error estimate of sigma squared is 0.4 divided by 4, or 0.1 for sigma squared, versus sigma squared is not estimated here because they don't give MS-res, versus about 2.7. All right. So the lack of fit estimate of sigma squared is something about. We'll see. I have to divide up the degrees of freedom. Okay, SSLOF is 24. So let's see. This number is SSLOF divided by 5, divided by the 0.1. Okay. But if I divide this by 5, I get about 5. Divide that by 0.1, I get about 50. Okay. So that's my F statistic. So FLOF. So, and I said, of course, the percentage point, the 5% percentage point of the F statistic with 5 numerator degrees. Actually, I have the wrong thing here. This should have been 4 denominator degrees of freedom. I made a mistake there. Okay, 4 denominator degrees of freedom. Okay. What is that? Equals. Yeah, I have it right here. Okay, I got the right number here. That's the percentage point of the F random variable with 5 numerator degrees of freedom and 4 denominator degrees of freedom. Okay, and so obviously 50 exceeds the 6 by a long way, and so you reject the hypothesis that there's no lack of fit. So you conclude there is a lack of fit, even with 99.5% explanation of the variability. Why is that? Let's have a look at the residuals. Or let's look at the fit. There's the fit. Okay? Let's have a look at the residuals. I have to compute those by hand now if I use this line S thing. That's the only problem. So the other tool is really much better. I just thought I'd show you this. My calculations, the predicted values, I have to do those by hand using these regression coefficients here. I used which ones did I use? Which table did I use? I guess I used. I can't tell which table I used, but those are the predicted ones, and these are the residual. Would it matter which table of betas I used?
As long as you use the corresponding correct xi, no.
Right. That won't. And so, in fact, these models will predict exactly the same. Okay, it's the same exact quadratic function. If I used, no matter which of these tables I use, as long as I use the corresponding x's. You see, it's the same exact quadratic function. So no matter what, all right? Same exact quadratic function. So if I want to extrapolate outside this data range, x goes from 4 to 7.3, it wouldn't matter which one of these sets of betas I used. As long as I use the corresponding x bar, right, formula, I'll get exactly the same prediction. So variance inflation factor kind of goes out the window here. There's nothing. It doesn't really come into play, except for the fact that the x prime x matrices might be difficult to invert and give you a round-off error. See what I'm saying? So you can talk about variance inflation factor, but the prediction will be identical with these two different sets. Now, there's less variability in one beta hat than there is in another. Okay? You see only 0.43866 over here versus the 5.4. So if you're interested in the betas themselves, okay, for some reason, okay, you want to estimate the betas only, okay, then to get smaller variability, you use the centered model, okay. So there's maybe a small reason why you'd want to use the centered variables, okay. Let's see. So I calculate the residuals, and there they are. Okay, and residuals for this trim residuals, not for the trim data. Did I plot the residuals anywhere? I didn't plot the residuals anywhere. Well, here I did. Residual plot. I got a -5, or close to a -5 for residual, and even after normalizing, I still would have 3 for a normalized residual. So pretty much I have an outlier there. Looks like the data fits really well, except for this one point. So I take that point out and see what happens. And then what do I get? If I take that number 9, remove it, look at my residuals now, and my error sum of squares, let's see, observation number 9 removed, let's see, I've got the little table here. My SS res is now 0.45. Now there's no lack of fit. And I have an R squared of 99.99. Okay, that's pretty outstanding. So this is a perfect fit. Here are the residuals, okay, for the trimmed data. I didn't do the standardized residual. There's still one. Now there's another one that's off, okay. Now, you know, because the fit is so close that you have a residual of -1/2. That's bad, okay. So the point is, you know, where is there a problem here? There's no problem at all now with observation number 9 removed. So even without investigating further, I would say just take it out. Okay, the fit is so tremendous. You'd obviously want to investigate and see what was going on with that data point. If this was real data, you'd say, well, it's a quadratic function, no question about it. Okay, it's an exact fit. Okay, what was going on with that data point? Okay. Even if you didn't know, you would still take the new, even if you couldn't figure it out, you would still probably take this new formula.
Nature, God's intervention.
Yeah, it could be. All right? So, any comments about this?
So, if with your second set of residuals that look a lot better, you still have, like, it's definitely not evenly weighted. Because there's that one that's kind of dragging everything down.
Yeah.
So.
Didn't you see that in your experimental data for problem 5.2 as well? Didn't you see a similar phenomenon? You had an exact fit, except for one point was kind of sticking out a little bit.
I don't remember.
That was on the Clausius-Clapeyron data for the vapor pressure.
No, that's not actually what I had. Not what.
Did you?
We had a pattern to the residuals.
Okay.
That was.
But how big was R squared? Wasn't it?
Oh, it was awesome.
99.99 or something.
And that's what I was like.
Yeah.
I put a note that's like it's insanely better, but there's still something unaccounted for.
Okay. Yes, you could still account for something. Maybe there was a quadratic correction or something. Okay.
Right.
So the residuals there had a pattern. Okay. Maybe it wasn't like this where just one was sticking out. The residuals had a pattern, but to first order, the model was an exact fit because of the high R squared.
Okay.
All right.
I was just wondering how you balance that. Like when you have numbers that are great, like an R squared.
Yeah, if an R squared is 100%, roughly speaking, okay, then you can make minor corrections, and you can have still funny things going on with the residuals, indicating yes, there really should be a correction, but the model is correct as it states because it fits so well. There's a whole other regime. Okay.
I can deal with that.
All right. Everybody who didn't do problem 5.2 might not understand. We'll have to go back and do that together someday. So why don't we quit this now and continue our discussions? Maybe I don't think I'm going to have to come back to this. All right, now we want to sort of, then you'll have we already did it, got second order polynomial in the first problem to study today. So you saw how I was playing with that. I had to be a little bit careful because there was not enough data to do a full quadratic fit to the catapult data. Unfortunately. All right? Where's the other half of the catapult? Also, maybe negative is possible if, depending on how they were measuring the heights from the catapult. What if the catapult was on a hill or something like that?
But then it would have been consistently done that way through the entire experiment.
That's true. But still, I mean, a negative might be a possible prediction.
Well, they said it was a distance, not a displacement.
Oh, that's right, not a displacement above the ground. Okay.
Yeah.
All right. I guess that wouldn't make sense either, displacement above the ground, unless the thing broke. Okay. We'll skip that. Side comment. Okay. Why don't we go on to splines? What is a spline? You're going to have to do one on your homework for next week, and also for your test. You have to do some kind of spline thing. But it's a very simple one. You have to do a situation where you're looking at a change point where you look at two lines, okay, two linear functions pasted together. That's an example of a spline. In general, a spline is just a bunch of polynomials pasted together. So, what is a spline? Is a piecewise polynomial function. And just to give an example first, to play with it a little bit, let's just define one and see where it takes us. So first I'm going to define the Heaviside function, capital H of x, to be equal to 1 if x is greater than or equal to 0, and 0 if x is less than 0. Some people make it undefined at x equal to 0, make it a half at x equal to 0, what have you. It doesn't really matter because we're not going to worry about single values that much. And an author puts it 1 if x is less than or equal to 0. Okay, and 0 greater than or, he uses different inequalities in this definition. He changes the strict inequality here and the non-strict inequality here, or whatever. Okay, I always use the one that's right continuous because that's the way we do it in probability. Okay, which is closely linked to statistics, so we better do it this way. I don't know why he does it the other way. Okay, h of x is this way, and then so let's define a function. Let's define f of x now to be the following, just some linear stuff, and then I'm going to put some quadratic stuff in here, and then I'm going to add a quadratic piece on the interval from x equals 2 to x equals 3. The way I do that is I can add a piece, and according to this formula, this piece is there if x is between 2 and 3 and it's 0 else. Right? Because h of x minus 2 is 1 for x bigger than 2. And h of x minus, it should be 3 minus x. What am I doing here? Did I write it down? No, I got it right here. H of 3 minus x would be 1 to the left of 3. Okay? So this is h of 3 minus x. This is h of 2 minus x. That way, and h of 3 minus x. So when you multiply those two functions, it become 1 on the interval 2, 3. Right? Make sense? So that I can just add a chunk here between 2 and 3. And and then I can add something else. Let's do something else. Plus a minus 1 minus 6 times x minus 3 for x to the right of 3. Okay, so there's a function. It's piecewise polynomial. Is it even continuous? Though.
It's continuous at x equals 2.
Because I wrote this as a function of x minus 2. This is 0 when x equals 2.
So it doesn't change anything there. But
okay.
At x equals 3, I can check it.
Okay, so how do we check it? Continuity. Check continuity. This is just to play with this representation a little bit. Let's see, the only places that you might have a discontinuity is at 2 or 3 because of the Heaviside function, right? Everything else is continuous. So f of 2 minus, we can actually we'll take the limit of f as x goes to 2 from the left. How would I do that? Well, I just plug in, when I have a continuous function, I just plug in x equals 2. So this is going to be 1 plus 4 plus, let's see, this thing is just going to be 0 when I plug in x equals to 2. So 0 times 0 times 1, if you want to put in these Heaviside factors. When x is just less than 2, this is h of a negative number. So that's 0. And this is h of a positive of 1. All right? Which is 1. H of 1 is 1. H of 0 minus is 0. H of 1 is 1. Okay? Heaviside only takes values 0 and 1. Then plus, let's see. I'm putting in x equals to 2 here. So I'm getting negative 1 minus, or plus 6. That's 5.
But it's times 0. 5
times 0. Okay. That's times 0. Excellent. What about f of 2 from the right? So that term is just going to be 0. And so this is simply going to be 1 plus 4 plus 0 plus 0 again. Because this Heaviside term is 0. And this term is 0 again because of this term. So indeed, we do have continuity at 2, as Shane was saying. What about at 3? What about at x equals 3? F of 3 from the left. Okay? Now I put in x equals 3, so I get 1 plus 6 for the first term. X equals to 3 here from the left. All right, well, one of them, let's see, this will be positive still. And this will be positive, right? 3 from the left. H of 1. This will be h of plus. Right? So that's 1 times 1. And I get something in here then. So this is plus. When I put in 3 there, I get 2 minus 3. And then times 1 times 1. Plus, when I put 3 from the left, though, this term is 0. This last term is 0. Because that's h of a negative, which is 0. So what do we get? We get 6. 1 plus 6 minus 1 is 6. F of 3 from the right now. Again, 1 plus 6 plus. Has this changed at all? Well, now I get h of a negative here, which is 0. So this term goes out. Plus 0. It's still 2 minus 3, but now times 0. Times 1 times 0. Okay? And while this term comes out plus, this is now a 1 now. But of course, this is a 0.
No, you get a negative 1.
This is a 0, and that's a negative 1. So this is negative 1 minus 0. So plus negative 1 plus 0 times plus 1. Okay, so this negative 1 contribution went out, but another negative 1 came in, so that I get still 6. Okay, so therefore you have continuity at x equals to 3 as well. Okay, so it's this kind of example. You want to see the function?
Yeah.
Okay.
I've got a picture going, and I think it's horribly wrong.
Okay. Let's see. I need my maple to come up. I need to draw a picture, and I need to make the function. Okay, so let's... Any comments about this?
You know what it looks like?
I know what it looks like, yeah. I could do it by hand. You want to just freehand it?
Yeah,
okay.
That's a rough idea.
Okay, the freehand actually is on his notes.
Oh, okay. Did not know that.
Okay. Yeah, I don't need the machine. On the bottom of the page 2. Thanks for reminding me that there's a freehand there. Okay. Let's repeat the freehand here. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And at x equal to 0, it's 1. So 0, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. This is the f. And I have as x. Let's see, it goes up to 5 at x equals to 2, I believe.
Yeah, we did that.
Okay, got this. Then, okay, I didn't show the rest of this. I didn't go through the slopes. But it's going to go, looks like this. Let's see. It goes back down to 5. comes back down to 5 at x equals to 3. Is that right? No, it comes down to 6. What did I do? I made the picture wrong, probably. Where's my actually good picture? Where's my good picture? Yeah, it goes like this. Oh, sorry. I made the picture wrong, so maybe you should correct it. It goes like this. It comes down a little bit. It goes to a value higher than 6. It comes down a little bit. It has like a, like a bill of a cap or something here. Okay? And then it comes to 6, and then it goes straight down to 4 by the time I get to 4. Because it goes down to 2 again. 2 at 4. Okay? Okay. So this slope, the slopes are not equal at these points. At these so-called knots, these are so-called knots, where you're making the junctions and making the change. You have continuity, but you don't have continuity of the first derivative. Right, this slope it turns out to be equal to 2. This slope is 4, coming in here. This slope is negative 2, and this slope is negative 4, I believe. I showed that. Yes. So it's a little bit more work. How would you actually do the slopes? What is the slope function for this curve? Derivative, okay.
So it's 2 from whatever 0 up to 2, because it's just the slope of the line.
Yeah.
And then
well, I went through the calculations here, but basically, what's the slope? The slope, this term is not going to give me any slope, right? At x equal to 2. At x equal to 3, it's going to give me something, okay? But x equal to 2, it'll only give me here. So at x equal to 2, I'll get this 2 as long as this function is...
You get 2x plus 2x, so it's 4 there.
Yeah. At x equal to 2, here, this is just 0, right? The slope, this hasn't even come in yet, okay? This correction term hasn't come in. So I'll get 2 plus 2 is 4 once I go past x equals to 2 here. All right? And stay to the left of 3 still. Okay? And then at x equal to 3, what am I getting for my slopes? Well, there'll be a contribution from this term for x less than 3, but not for x bigger than 3. For x less than 3, what does this contribute for a slope? 2 minus 6 times 1, which is a negative 4. For x less than 3, so it's 2 minus 4, Yeah, that gives me, 2 plus 2 minus 6 is a negative 2. All right? For the slope just to the left of 3. And for x bigger than 3, this doesn't contribute, but that one will. They give me another a negative 6, so then I get 2 minus 6, okay, for a negative 4 to the x bigger than 3. Okay, so there's the function graph. All right. Now, how would I make a function that has? Now I need to make a definition because I want to formalize. This is just kind of playing around. All right. Now I want to actually try to make things a little bit more organized. How will I actually organize and how I actually write down these splines? If I was going to make a regression model for them, what would I do? There are various ways to do it. I mean, as you can see, I could get this. I could probably write this function up, several different ways. Right. So now I'm going to define the following: x minus t plus is defined. The positive part of x minus t is x minus t times h of x minus t. That's the definition, which is equal to x minus t if x is bigger than or equal to t, all right, and 0 else. If x is less than t. So if t is a fixed number, and I'm looking at it like that. And so let's see, what would be in x minus t to a power? I could just put the power here. If I put k here, for k greater than or equal to 0. All right? Or even for negative powers, but we're not going to consider it negative powers. So with the 0th case would be just the Heaviside function again, right? X minus t to the 0 would just be the Heaviside function. Actually, this should be a k here. Would just be the Heaviside function again. H of x minus t. Okay, so that's the definition. So you get the powers of the positive parts and so on. So let's see if I can find a cubic spline with two continuous derivatives. Cubic spline just means it has some cubic terms in it. Okay. What did I do here? Did I write this right? I hope I did. Okay. I put in f of x equals 1 minus x plus 12x squared minus x cubed minus 12x minus 2 plus cubed. Okay. So it's a cubic function, then it's another cubic function for x bigger than 2, and then yet it's another cubic function for x bigger than 3. And x less. So you have basically you have the intervals x less than 2. It's cubic. So for the interval 0 less than, well, let's just put x less than 2. You have 2 less than x less than 3. And you have x bigger than 3. It's cubic, and then it's cubic unless I cancel the cubic nature. But I'd have a 12x cubed. I don't think I can cancel that. Okay, and then I'd have another cubic, and I haven't canceled the x cubed, so it really is cubic. I don't believe I've canceled the x cubed. Okay, no. Now, how would that actually graph out? And how do I know it has two continuous derivatives? How would be the derivatives of this function? Okay. Sorry about that. What are the derivatives of this little function?
Alright, so just so I understand this right, when x is in between 2 and 3, then our function is minus x plus 12x squared minus x cubed minus 12 times x minus 2 cubed.
That's correct.
Okay, cool. Just wanted to make sure that I got it right.
Right. So it's this piece for x less than 2. It's just take the first cubic expression, and then and for x between 2 and 3, wherever the next knot is, you have this expression, and for the whole gizmo, it's this without the plus signs. Do you understand what he's saying? How he's writing it? You have to add more terms and cancel terms and so on to actually recalculate what function it is.
So continuity is really easy to show, and that's you got that immediately by having the x minus 2
right.
and the x minus 3. So all we have to do is show that the first derivative is continuous, or we want two continuous derivatives?
Yeah.
Showing the first derivative and the second derivative?
Yeah. So what are the derivatives of these functions? What's the derivative of something like this? Is that kind of obvious what that is? Can I actually do that by calculus? Can we take the derivative of that?
Okay. K is an integer, right?
Obviously, when away from the point anyway. I mean, let's see, how does this work? Yeah. So in other words, for k greater than or equal to 2, I believe you can differentiate that thing, right? Let's see, what would it be? So if I took x plus squared, okay? What is that? That looks like it's 0, and then it's the parabola, right? Y equals x squared. So what's the derivative of that function?
0 up to...
It's 0. It's 0. Obviously, it's 0 for x less than 0. Okay, it's 2x for x greater than 0, but it's also, the derivative is well defined at x equal to 0. All right? So d by dx, x squared plus, is equal to a nice continuous function, 2x plus. Okay? That's a continuous function. Okay, and you can do it for all k greater than or equal to 2. You get a continuous function. So it's not too hard to differentiate this thing. Okay. So that one automatically has 2 continuous derivatives. Maybe we should plug that in and make sure. Everybody want to see it? Now you'll get to say, oh, now show it with Maple, please. Okay. So I guess I did a different one on the picture here, but I guess it'll be just as good. So first I need to define what the Heaviside function was. I didn't want to write out Heaviside every time I wrote Heaviside. So I just took this Maple worksheet and first I defined capital H to be the Heaviside function. Okay, because I didn't want to write Heaviside every time I wrote it down. That's the first line. Okay. No, I didn't put this. I just threw this up as a Maple sheet. But I did give you some examples. But on your printouts, I gave you some Maple examples. I didn't do this one particularly. I don't think yes, I wrote out Heaviside longhand on this one. I don't know why I did that. So I'm just checking to make sure I got the right function. H of 0.005 is 1. H of negative 0.005 is 0. All right, so my function's working, and I plug it in. Let's see what I do here. 1 plus 2x minus 3x minus 2 squared h of x minus 2 plus 3x minus 3 squared h of x minus 3. A different one. Okay. And then I plotted it. So that's continuous and has 2 continuous derivatives. If I had plotted it... What did I say the other one was? I forgot what it was. But anyway, that's good enough, I suppose. You want to play with it at all? You can change these however you want. You still get a continuous... You get concavity throwout. So if I put in 30, that's probably going to mess it up a lot.
Don't you have to put it in over...
Oops, that's totally messed up.
Section?
Yeah, I have to put it here. Okay.
Now, these are just squared terms, so they're only going to have one continuous derivative?
What's our only squared? Oh, this is squared only. Yeah, this is only one continuous derivative. This only has one continuous derivative, right. So this is quadratic. What did I do? This is linear, then quadratic, then quadratic. So all I did was squared terms here. Linear, quadratic, quadratic. You want the cubic terms? Then this is linear, cubic, quadratic, and then cubic. I guess we could do that. Maybe I should just take the 12 off and make it a cubic. So let's make this a cubic. Okay. Linear, quadratic, cubic.
You're going to need to get rid of that extra star.
What did I do here? Okay, you're right. Linear, quadratic, cubic. That's not so exciting. Okay. I needed x goes from 0 to 5 maybe, and 0 to 6. Okay, it's starting to be more interesting. Okay, linear, quadratic, cubic is that one now. You want to see the derivatives? Okay.
It's easy.
Well,
like this one should have a continuous first derivative.
I need to. Okay, so
Discontinuous second derivative somewhere. Right.
Okay, so what do I need? I need to define f prime. Fp equals that didn't spell diff right. I think I know how to do maple. I don't know if I still know how to do maple. With respect to x, do I have too many parentheses? Unapply. How many parentheses do I have? F of x. Is that good? That should give me invalid.
Try getting rid of one of the parentheses after the f of x.
Yeah.
Because it should be f of x, comma.
Oh, you're right. Are you sure?
I have no idea. But
Oh, I see. No, I need an extra one after that. This, that's what I need. Because the derivative of fx with respect to x and then as a function of x. Okay? That gives me Dirac. Okay? I hope he doesn't plot Dirac. Okay? Okay? So then I need to plot f prime. Thank you for the help. As a function of x. X goes from 0 to 8, let's just say. Constant, linear in this piece between x equals, okay, so it's constant and then linear and then it's quadratic. But it's still continuous. Okay? This will only have one continuous derivative because I had a squared term, right?
right.
Okay. All right. We're done maple for the day. Okay? See, we need one more example, I think, before we can call it quits today. I hope I have one more example to give you. Otherwise, I have to pull out the distribution theory. I'll have to do that. Okay, so so let's do exercise 7.10. I think we should be ready for that one now. Are you going to run out of time on that, Radu? Okay, according to this problem, exercise 710, we want to model a piecewise polynomial with 3 segments. Linear on the first segment, quadratic for the second segment, and linear for the third segment. All right? So we want to let that 0 less than t1 less than t2 and say model EY equals S of X, linear for X less than T1, quadratic for T1 less than X less than T2, and linear again for T2 less than X. I know, that's probably why I had that picture up there. I know, maybe I will have to go back to that one. I will have to go back to the picture one more. For X less than T, for X bigger than T2. That's the way I want it. Okay? And what the author suggests is writing out the general full quadratic business of quadratic, then quadratic, and then quadratic as follows. With actually possible discontinuities. Alright? Quadratic, quadratic, quadratic would look as the following. S of X is equal to beta, here's the way of writing it down. Beta 0, 0 plus beta 0, 1 X plus beta 0, 2 X squared. 0 for the 0, excuse me, 0 for
The first segment, the first section.
yeah, I guess for T0.
T0 to T1.
T0 to T1, something like that. Yeah, so we could do it for T0 less than, to make the notation a little bit more consistent. All right. Plus B10 X minus T1 plus to the 0 power plus B11 X minus T1 plus to the 1 power plus B12. Second index corresponding to the second power. Okay. Also, you can introduce these as regressors. You can introduce 1 as a regressor, x as a regressor, x squared as a regressor. You can also look at the positive part of x minus t1, which to the 0th power, which would be, let's see, if x is bigger than t1, you get 1. If x is less than t1, you get 0. So it's 1s and 0s is the column. 1s and 0s, so just like the Heaviside function. Okay? And then, powers here of the x's, x minus t1. If x is bigger than t1 and 0, if not. All right? And so on. Okay? So you'll get anywhere where x is less than t1, you'll just get zeros in these columns. Okay? When you actually write down the regressors. So it will be consistently 0 in each of these 3 columns. So everybody, I don't know, we didn't do that, but you'll have to do it for your homework. Okay. Now, plus then the third case, I'm also introducing here a beta 2 0 on the last segment, x minus t2 to the 0 plus beta 2 1. X minus t2 to the 1 power with plus and plus beta 2 2. X minus t2 plus squared. That. Okay. So this is the spline. I don't know how you do splines with more variables than one variable. I haven't thought too much about it. Pasting surfaces together would be kind of a pain, I imagine. Okay. So we're definitely working in one dimension here. Now, so I said this is the general quadratic. The first question is, how do you set it up so that it's linear, quadratic, and then linear?
So we can get rid of the quadratic first one, b02 is equal to 0.
Okay, this one. Okay, so part A, make beta 02 equal to 0.
And then we can make beta 22 equal negative beta 12.
That's very good. Very good. Beta 22 equals negative beta 12, because you want to kill the quadratic. You have a quadratic x squared term here, right? With a coefficient beta 12, there's no other quadratic terms around. If there had been one for the first one, you'd have to, for example, if you'd had the first piece quadratic, you'd have to have beta 10 plus beta 12 equal to minus beta 22. Okay, you'd have to kill both of them off. You understand? You understand what I'm saying? So you had an x squared here, another x squared here, then you'd have to put a negative 2x squared there. All right? To kill them both off if you want to get linear on the last piece. But we're assuming that there's only linear on the first piece as well. Okay? I might as well divide it up like this. What happened? Wrong place to divide it up. Here. Okay? So here's my second quadrant. Here's my quadratic contribution. I'm kicking in an x squared term. All right? I have to kill it. I have to kill it off. All right? Here. So beta 22 equals minus beta 12. That's to make, just to get the modeling going. Okay, now how do I make it continuous? So now assume A holds. Make it continuous.
Get rid of the not term.
Yes. This term is how much the function jumps by. This would be a discontinuity. So beta 10 would be the jump. If I had a linear expression and then beta 10 would be the jump for this next quadratic piece, this would be beta 10. Okay? Be the amount of the jump. Okay? And then I had another, linear piece, I guess. This would be the beta 20. Would be a negative number in that case. All right? So then you just make the beta 10 equal to beta 20 equal to 0. Okay, last part. How do you make the first derivative continuous?
Get rid of the linear terms.
Yeah. So that's pretty much everything else. Okay. So then you wouldn't have So yeah, you would get rid of the linear terms for that, because what we're saying is this: if I take the way I argued it is this: S prime of T1 plus minus S prime of T1 minus. This is the way to argue it, to organize the argument. There's nothing going on here because this function hasn't even come in yet when we're at x equals T1, right? So, and since the derivative, this part, okay, the derivatives are being differenced, the derivative of this function is continuous, okay, at x equals T1. So those are differenced off, so I'm only getting this term, okay. We're assuming that beta 1 equals to 0. Beta 1, 0 is equal to 0. And we already know how to differentiate this and saw that it was continuous. Right, so that wouldn't have any contribution. So that would be just the beta 1, 1. These are limits. So actually these do make sense. This is a limit as x goes to T1 from the right. This is the limit of the derivative as x goes to T1 from the left. So these actually are meaningful. Okay? These limits are meaningful. The derivative doesn't exist at x equals to T1. Because you have that, this is the Mach absolute value function. You have this for x plus. Okay, that doesn't have a derivative at x equal to 0. All right, it's undefined, but the limits exist. Okay? Okay. All right, so you get beta 1, 1 there, and similarly over there. Okay, you get beta 2, 1. So for part C, to make S prime exists, S prime x exists everywhere if in addition beta 1, 1 equals beta 1, 2, 2, 1 equals to 0. Okay, so what does that give you left? If we did that, you've got this gone, you've got this gone, you've got this gone, you've got this gone, and you have beta 2, 2 is minus beta 1, 2. So that's the end. Okay? And actually that's the first example I showed you when we had the maple screen up there. Okay, should I show you that one more time? I had exactly the situation where I had a quadratic function, all right, where I had plus 3x minus 2 squared with the plus sign, and then minus 3x minus 2 squared. X minus 3 squared, sorry. So I had this. I had, I don't know what I put in for the first function. I can't remember. 1 plus 2x?
1 plus 2x.
X minus 3 plus squared. So this coefficient has to match this one to have the continuity of the...
or to be linear again. To be linear on the far side.
Yeah, to be linear on the far side. That's what it is. Okay, that's the way I had it. Okay, example. All conditions hold. Okay, so fairly simple. Now at least you can work your way around this stuff. And I think I gave the maple pictures. Okay, I didn't do this example, but I gave some pictures. Any comments at this point? Ready for? I think I'm going to skip doing the full factorial quadratic model right now. Any more questions about the exam? You got that due on Wednesday.
Question.
Yes.
On number 4A, when you say introduce an appropriate design of this as, is that about those phoenixes we were working with? On the general linear?
Okay, let's have a look at problem 4A of the exam. I don't think I have a copy. Yes, I do have a copy of the exam on the website. I just thought for everybody to refer to the same thing so we could get it on camera. That's good enough. Okay. Okay, so here's the spline problem. Okay. You would have to ask that. Consider the expanded computer repair time data, which is on. Whoops. Oh, I should just save a copy to the desktop. So I can save it. Okay. Then I can go back. Okay, computer repair times was. Where was the computer repair? Lack of fit analysis for computer repair time data. Already exists. Okay, I didn't need it open. There it is. And what I was looking at is this expanded data set right here. Okay, expanded data set for the computer research. Okay. But I already did the lack of fit analysis. Okay. I just want you to use that particular data. Okay. As you can see, here's the line, a single line for the trivial spline. Okay. Fit to this data. Okay. Okay. So what I want now is to consider that data and it's shown to exhibit a lack of fit. Now, fit the following change point model. That's the idea of the spline. We didn't have a name for it before, but anyway, fit now the following change point. Okay? So it's two different linear approximations. All right? One for x less than or equal to 10, one for, so x equals 10 is the not. Okay. Test the hypothesis and so on by using the extra sum of squares method. So what's the question? By introducing the appropriate design matrix X.
Is that the T matrix we're talking about? The design matrix? I'm not sure what that
X is what I always call X is the matrix, right? So usually had a column of one. Usually had a column of ones.
Right.
All right. And then some other columns. So what would be the X matrix for one of these spline models?
That's where you have to apply the heavy side condition to it.
Yeah. Let's see. I must have one of those somewhere.
You did it on this same data when you
Computer repair time. Yeah, I just have it there. Where is my? Here it is.
I don't know if you still have it on that one. No.
I didn't do anything there. Okay.
Well, you had it before.
I did? Okay. I changed it. Yeah. Okay. So what do I need? I need an Excel document. How do I do?
You need a couple more rows or a couple more columns next to X, right?
Let's say I wanted to have. I don't want to show you the whole problem. Let's just do this. How do I do X minus? I guess I just have to show you. X minus 10, so plus. Okay? How do I actually get that? What does that look like?
Equals if.
I should take it this. Yeah, edit, cut. Put it down here, because that's where I'm going to do it for this data set, right? Insert a column. Put it here. It won't paste it anymore. Okay. Okay. If.
Yeah, equals. If, open parentheses, select X, the arrow over, and is greater than. And comma. Nope.
I messed it up.
You have to click OK before to let you know. Okay, comma. Then, well, that'll be what it is if it's true, and then comma, what it is if it's false.
Okay. So yeah. So then put it's true. Okay. Then this. I don't need a then. So let's just put this. This was. So actually, I need.
One. Put in X. Put in.
I need to put this again.
Yeah.
Okay. And then else. Put in 0, right?
Yeah, but you need to put in C53, not 1, and didn't take it. Hit return now.
Okay? Now I should be able to pull this whole thing down.
Yep.
It should give me X when X is bigger than 10 and 0 when x is less than 10. I don't know what it does exactly at 10. Yeah, because I put strict greater than equality, so it gives me that. Okay? So here's the formula again. That was for the 1 power. For the 1 power. If I want the 0th power, then I would have put in 1 in 0, not C56 in 0. If I wanted the square power, I'd put C56 squared in 0. So the Heaviside function itself, of course, that's trivial practically, but 2 to 0, okay, then I would put this is 1, right? And then I could pull this whole window down, and I get zeros and ones. That's the Heaviside function. Where I put in, this says if, and then evaluates this is true or not. Okay, if this is true, then go ahead and put in whatever this next argument is. All right, and if it's false, then it puts in whatever the third argument is. All right, that's how the if works.
I'm not exactly sure how to do greater than or equal to in that notation without using an or.
It doesn't do it. Okay.
It carries all the way down to
yeah, what you can do, yeah. Oh, really?
Yeah.
Oh, okay.
Adjust the first one.
All right. Oh, I see. Right. Whoops. Let's not do that.
Yeah.
I'm terrible with these things.
So, okay, so it does use that.
Okay.
What you do, just
Greater than equal. Okay? We're all settled. Now you can make Heaviside functions and other things. So that's what you're going to do. You're going to need, what is it in this problem? I claim, I already told you how many 4 columns it has. 4 columns. I claim there's 4 things to put in there. Because what is this? This is your alpha 0 for x less than 10. That's your x minus. That's your x plus to the 0. Here's your x plus to the 1. Here's your x minus 10 plus to the 0. Here's your x minus 10 plus to the 1. Only 0th and 1th powers. 2 0th powers, 2 1th powers. Okay? There's 4 columns. So you don't put an intercept column in. Okay, I think that answers that question. It tells you the problem. Okay, you should all be able to get this problem right now. Everybody happy? Yes. Questions? We'll do one of these Heaviside things on Monday, so you can see it. Okay. We will have a meeting on Monday. We'll probably leave a little early since it's a holiday, but officially we're going to have it. If there's no camera that day, there's no camera that day. It may not be because somebody might not show up. There won't be probably any camera on the 24th of July either when the final exam is scheduled. All right?
Well, I should be here on Monday because my class is canceled. So.
Okay. Excellent. That's it for today then, folks.
I've got a question.
Yes. You have another question on the exam?
Yeah. Are you pretty much explicitly asking for the stuff that you want, or are we supposed to?
Hey, did I ask for everything? I went through the problems, and pretty much sort of figured out what I was going to figure out. But if you figure out something different, let me know. And I think on problem number, it says in comment on the residuals and so on. So comment on these residuals. I think in 5A I didn't ask you about the standardized residuals versus the predicted values, and I mean to say comment on them too. All right, you should make some comments in 5A. I think I kind of skipped saying something about that. Yeah, I think it's pretty much I asked for everything I wanted. But if there's something that doesn't seem to fit what you're thinking is, I think most of them are problems out of the book, except for my computer repair time thing. And problem 1 was also like a problem out of the book, only made it much more explicit exactly what I wanted. Okay, so I tried to improve the problems from the book, in essence. And then I had my computer repair problem, and so on. Okay.